So first of all, I'd like to ask Professor Shashua if it's okay if we start 5 minutes early rather than at 9:20. Would you be ready to start? Okay. So let me first give an introduction to you before calling on you. Amnon Shashua is the Sachs Professor of Computer Science at the Hebrew University, and he's also an executive at Mobileye. He's a computer science professor in Jerusalem, as well as co-founder of Mobileye and co-founder and CTO of OrCam. As of the Intel acquisition of Mobileye in 2017, he serves as CEO and president of Mobileye and senior vice president of the Intel Corporation. He's been on the computer science faculty at the Hebrew University of Jerusalem since 1996. And he's been a full professor since 2003. He's been head of the Engineering Computer Science School at the Hebrew University and currently holds the Sachs Chair in Computer Science. Over the years, he's published over 100 papers in the field of machine learning. His work includes early visual processing of saliency and grouping mechanisms, visual recognition and learning, image synthesis for animation and graphics, theory of computer vision in the areas of multiple view geometry and multi-view tensors, multilinear algebraic systems in vision and learning, and primal dual optimization for approximate inference in Markov random fields and graphical models. And since 2014 on deep layered networks. His work on multiple view geometry received Best Paper Award at ECCV, and his work on graphical models received a Best Paper Award category at UAI. He's received a number of other prizes before being named to his current chair. I'll just mention one particular reminiscence from a colleague at Hebrew University. When he co-founded Mobileye, he told a colleague that he aimed to start a $100 million company. As it turns out, he was short by 2 orders of magnitude. Despite the many responsibilities that he has as an executive at Intel and Mobileye, he's still mentoring PhD students and he's active at the Hebrew University. He's driving a huge growth of artificial intelligence in Jerusalem, and he's made Intel agree to base all their autonomous driving activities there. So we're very fortunate to have him here today to inject his viewpoint about the current state of deep learning. Thank you very much for coming here, Professor Shashua.
Thank you, David. It's a slide I took from NVIDIA's website. It shows in a nice way that computing is everywhere. Today, computing is machine learning. Machine learning is called AI, and it's really everywhere. And we all know that technology is application of science, but when it comes to deep learning, technology has a life of its own. I think David mentioned that there are certain areas in deep learning in which all what counts is only data and resources that are not available to scientific explorations. And the question is where does fundamental science come in when we're looking at artificial intelligence? And I'll say a few words about that. And I'll then talk a bit about where deep learning are impacting other branches of science. And then the bulk of my presentation will be on autonomous driving. I think autonomous driving is an excellent microcosmos to all issues of artificial intelligence. You have perception, you have decision-making, multi-agent decision-making. You have issues of ethics, because you want to guarantee that there will be no accidents. How do you do that? So issues of ethics. And then at the end, you have control. So it's all integrated, all problems of AI integrated into one very, very interesting application. So I'll spend most of my talk on that. And then if I'll have time, I'll mention what I think is the next frontier for AI, which is natural language understanding, and what are really the key issues there. So I'll start first with the mysteries of deep learning, where really fundamental science, there's lots of fundamental science to be done in deep learning, and then I'll mention one key mystery. The next slide has equations, but that's the only slide with equations. After that, there are no more equations. So just to set up the stage, when I'm talking about machine learning, what I want here to clarify is the difference between the classical machine learning and deep networks. Where is really the mystery coming in? Because classical machine learning is really well understood. With deep networks, we have some mysteries. So when we're talking about the setup, we have the input space. Input could be an image, could be a sound wave, could be a text. Then we have a label space. Label could be binary. Does the image contain a cat or not? Or could be multi-labels. You know, there could be 1,000 categories. Which of those categories you find in an image? And then you have a distribution of the input and the label space. And then you have a loss function. You have the true label and a predicted label. The predicted label here is y hat, and you have a loss function. Right? So the task is that you are given a training sample, so a pairs of input and output drawn from this unknown distribution, and you want to the learner needs to generate a mapping function from input to output. And you want to minimize the prediction lost, which is kind of the expectation over draws of input output from this distribution on the loss function. Okay. Now, since we don't have the distribution, the approach is you define a hypothesis space. You're kind of tying your hands rather than looking at all possible functions. You're looking at a reduced space of functions. That's a hypothesis space. And you, instead of minimizing the true loss, you're minimizing the empirical loss. You're simply looking at the training set and minimizing the loss over the training set. So this is kind of the setup. So what are the key elements? So if you look at this drawing, the outer box is the entire space of functions. The inner box, H, is the hypothesis space. Now F star D is the true function, which could be outside of the hypothesis space. H star D is the optimal function in the hypothesis space, and the difference between them is called an approximation error. So if you increase the hypothesis space, you reduce the approximation error. H star S is the empirical, because we're optimizing over the training set. We're not optimizing over the true distribution. So that's the empirical function that we find, and the difference between that and H star D is called estimation error. That's the ability to generalize. And then if the function that we want to optimize is non-convex, there is no guarantee that we'll find H star S, so we'll find H bar, and the difference between those is the training error. Okay? So this is kind of the setup. If you look at classical machine learning, support vector machines, the hypothesis space is linear, and then there are this kernel trick which allows us to work in feature space, which would give us nonlinear functions. And all of that is really well understood. And if you look at this particular space, there is no training error because the problem is convex. It's a linear hypothesis space. So there is no training error. And then what happens there is very intuitive. If you increase the hypothesis space, if you expand, then you are reducing the approximation error. And at the same time, you are increasing the estimation error. That means your ability to generalize gets reduced. And you can see this even pictorially. Imagine in your mind that you are increasing this H. So on one hand, you are reducing approximation error, and on the other hand, you are reducing estimation error. And if it shrinks, it's the opposite. If you shrink it, you are tying your hands more and more, then approximation error increases, but then you generalize better. So, and then this is well understood. What happens with deep networks, with deep networks we have fully connected layers, we have recurrent networks, RNNs, and since 2014, 2015, we have a zoo of different architectures of networks, whether it's ResNet and GoogleNet, Inception networks, and so forth and so forth. With these networks, what is the real mystery? The real mystery is that stochastic gradient, so the problem is non-convex, but stochastic gradient descent somehow gives us good solutions. But the real mystery is that when we expand the hypothesis space, that means we're creating over-parameterized networks, we are reducing the approximation error, but at the same time, we're also reducing the estimation error, which is kind of counterintuitive. So when we have oversubscribed networks, which you would feel that all what they will do is overfit, they actually are not overfitting, and that's based on the kind of data that you feed them, right? And this part is not well understood. So there's a lot of fundamental science to be done, even though they work quite well, but from a scientific point of view, there are many things that are not understood there, and if we understand them correctly, we'll be able to expand this field to other domains. Other branches of science, I'll say a few words about that. Specifically, the connection to condensed matter physics. A few weeks ago, my lab, we published a paper at the Physical Reviews Letter, PRL. And it's interesting because computer scientists publishing a paper in a premier physics journal, you'll not be able to do it if you're not making a contribution to physics. So how do deep networks make a contribution to physics? So when we look at pictures, now we are interested in correlation among pixels. In physics, correlation is entanglement. So there's entanglements among particles if you're looking at a many particle body. So pixels and particles, and you can make a connection between deep networks and the kinds of tools that physicists use in order to represent highly entangled systems. Those tools are called tensor networks. Now, many interesting phenomena in nature, if you look at many particles, are highly entangled, meaning that they are not just correlated in a cascade manner, but large groups of particles behave as one group. And in order to simulate that, you need to simulate a system with many particles, because if you simulate a system with a small number of particles, the edge effects, the boundary conditions, they kind of dominate, and you don't see the true observations. But if you look at many particles, you have it's an exponential growth. When you look at the wave function, it's very, very difficult to simulate. So what we found out is that you can have a direct mapping, a one-to-one mapping between deep networks, the convolutional networks that we use, and the tools that physicists use in order to approximate wave functions, and these are called tensor networks. And then you can prove a theorem that you can be polynomially more efficient than any of the tools used today by physicists if you use this mapping between convolutional networks into tensor networks. So this is an example of a contribution of deep networks to other branches of science. Since the publication of this paper in PRL, we have another work that shows that we can also optimize in exponentially more efficient, very, very large systems, again, using concepts from deep networks. Okay, so now I'll go to the main part of my talk, and let's look at autonomous driving as a microcosmos to artificial intelligence. Because I think autonomous driving really exemplifies all the issues that you have, and also it has a very, very clear goal. It will save lives, it will disrupt transportation as we know it. There is a very, very big business around it, so there's very strong motivation to make it work. And the question is what are the key issues of making this work? So when you look at that autonomous cars, there are two main building blocks. One is perception. We have cameras, we have other sensors feeding raw data into microprocessors, and we need to apply AI in order to perceive the world, know where vehicles, pedestrians, traffic signs, traffic lights, drivable paths, everything around the car 360 degrees, we have to understand it at very, very high levels of details. And this is mostly data-driven imitation learning, right? We want to imitate the way humans, the performance of humans, and we have labeled data. It's difficult to generate very, very large amount of labeled data, but this is what companies are good at. You have lots and lots of resources, so you can generate lots and lots of data and label them. Right? So it's mostly supervised learning. But then once you perceive the environment, you need to make decisions, and it's a multi-agent game, right? Because your decision, whether you want to accelerate, brake, turn the steering wheel, affects also other agents. Right? When you change lane, somebody needs to slow down. So you are affecting the motion of other agents. So it's a multi-agent game. And here you want to optimize smoothness. You want to optimize agility to be able to merge into traffic. But on the other hand, you need to be safe. And this is where ethics come in. Right? So when we look at the perception, right, you know, a perceptual mistake can lead to an accident. You need to make sure that if this happens, it does not exceed human probability of creating an accident. Because to enable human driving, society has no choice, right? Because without anyone driving, we'll not be able to go anywhere. But society has a choice whether to enable robotic driving. So society will not accept a robotic car in which the probability of an accident is higher than a human driver. So the first thing that we need to make sure that, you know, from a perceptual system, a perceptual mistake that leads to an accident should not happen at a higher probability than with humans. Then with the driving policy, say your perception is perfect, but now you are making you have a lapse of judgment. You are making a driving policy decision that leads to an accident. This should never happen. And the question is, how do you guarantee this? This should never happen. The only thing that you're allowed to happen is at an infinitesimal probability to have a perceptual mistake. And now the question is how these two work together when you build a system. So just to remind us all what it means to drive, this is a drone that I took over my way to work. And you see that's really difficult, right? I'm not showing you a crazy place like in India or some places in Asia, but you know, this is similar to France, Italy. The car now is trying to merge to the left and kind of does not succeed, right? We're fast forwarding the clip here. All right. And you know, later this large truck will try to merge, and we're fast forwarding. It will take a long time until this poor guy can merge into traffic. So there is a strong need for agility, right? But agility introduces the risk of an accident. So how do you balance the two things, right? So it's a very difficult issue. So let's look at the driving policy challenge. So let's assume our perception is perfect. We understand, we perceive the world accurately, and now we need to make decisions. So what is really the challenge there? Do we allow an accident due to a lapse of judgment? I don't think this would work, right? We need to build technology that doesn't have any lapse of judgment. Should the occurrence of lapse of judgment measured statistically? This is also problematic. The amount of data that you'll need to collect would be enormous in order to validate, and then any change you make to the software will need to be really revalidated. So the conclusion is that when you're talking about safety, it's really outside of the machine learning. It's outside of something statistical. It's like the 3 rules of robotics of Asimov, right? You want to have a formal model that will give you guarantees that you'll never have a lapse of judgment. And here it sounds tricky because there's a lot of common sense in our judgment of driving. How do we go and formalize this in a way that would be useful and would comply with the way humans drive? So it's kind of the ethics of AI, kind of a set of rules that on one hand will allow agility, on the other hand would guarantee safety. So it all boils down to what it means to be careful. Because you can come up with all sorts of definitions of being careful that sound, very, very legitimate but are not useful. For example, when I change lane, I can define carefulness as if I change lane, no other agent should be affected. They should continue with their same speed and velocity. That sounds very, very safe. But if we do that, we'll never be able to change lane in congested traffic, because I change lane, somebody needs to slow down. Right? So we need to find definitions of being careful that allows for agility, and on the other hand, we can build a model, a formal model around it, and make guarantees around that model. So this is a challenge that we took a year and a half ago. We published a paper with my colleagues. Shai Shalev-Schwartz is also a professor at the Hebrew University. And we tried to formalize. What we did there, we understood that there are three dimensions that you want to optimize. You want to have a model that is sound. It means it complies with the human judgment, with the common sense of human judgment when driving. That means when the model states that something is careful, humans would always say, yes, this is being careful. On the other hand, you want to be useful. The example that I gave sounds like a very legitimate way of defining being careful, but it's not useful. So you want a model that allows for usefulness, allows for agility. And the third one, this is where formality comes in. You want a model that you can prove things on it. For example, if the model makes an action and determines that this action is safe, if in order to prove that the action is safe, you need to roll out the entire future, because there could be butterfly effects. You can have an innocent action now, then there'll be a chain of action, reaction, and then an accident 5 minutes later is going to happen, and that accident is tied to the innocent action you made right now, then you'll never be able to validate. So you basically need to build a model which the inductive principle applies. That means if this action is safe, you can prove that it will never create an accident in the future. So this is where the formality comes in. So this is a challenge. At the model we call it RSS, Responsibility Sensitive Safety, and it goes into the path planning. So the driving policy logic comprises of two elements that are machine learning based. One is strategy. The system needs to make a decision whether we want to change lane now. That's a strategic decision. That's based on machine learning, reinforcement learning. The second one is tactics. Once you decided to change lane, you need to make a decision which vehicle you are giving way and which vehicle you are taking way. And the gap between those two is the gap that you want to enter. And this changes every fraction of a second, because let's assume that you decided to take way from a vehicle on your left, but that vehicle doesn't allow you to take way, then you need to change your decision. So that we call tactics, and this is also machine learning, reinforcement learning. The path planning is governed by this formal model to make sure that the system never makes a decision that will create an accident based on the RSS, and then you have control. Let me go about the second challenge before I show examples. So the second challenge, called this the perception challenge. In the perception challenge, the world is rich with details. Both dynamic, vehicles and pedestrians, and also static, drivable path, whether there is a road edge, and so forth. So first question is today AIs, today deep learning, can we cope with the details that we need to perceive? The answer is yes. It means you see this everywhere. There isn't any perceptual task out there that with enough data you cannot really be able to solve it. The question is what defines solving it? And in this space, solving means reaching a sufficient accuracy. So to understand what reaching sufficient accuracy is, let's do the following thought experiment. Right? We know that the accident statistics with humans is a probability of a fatality per 1 hour of driving is 1 to a million. Now, if we remove driving under influence, and if we remove driving with, texting while driving, because machines are not going to drive under influence, and they're not going to text while driving, so it's a safe assumption to make that it's 10 times better. So 10 to the minus 7. So that's the probability. If this is the probability, the mean time between failures that we need to prove is 10 to the power of 7. So we need to drive 10 million hours of driving and show that we never had a perceptual mistake that led to an accident, that led to a fatality. Now, to understand the sheer magnitude of this, let's look at driving assist. Look at driving assist. AEB is autonomous emergency braking. This is now on almost every new car out on the road. These systems, they use perception in order to detect whether an imminent accident is going to happen, and if so, the car emits warnings and then actuates the brakes before a collision. And you need to reach very, very high levels of fidelity, both in terms of the probability of a false negative, of a misdetection, but more importantly, the probability of a false detection. Because if you have a false actuation of braking, it is really scary, right? You know, driving leisurely in your car and all of a sudden the car brakes without any reason, that is something very, very bad in terms of the reputation of the car maker. So there's a lot of effort on reducing the probability of false positives. And the question is where's the industry in that respect? So the industry in that respect is in a very good position that you have a false positive, a false actuation once every tens of thousands of hours of driving. That's very, very good. Tens of thousands of hours of driving, you'll not have a false actuation. But this is 3 orders of magnitude lower than what is needed. We need 10 to the power of 7. And that is only false positives. In autonomous driving, false negatives is more important than false positives, right? Because if you miss a target and you hit it, you create an accident. So we're talking about something that is really far away from the best technology out there, and the best technology out there uses deep learning, right? Everybody's using deep learning. So the way to handle this is to break down this MTBF into subsystems. So one subsystem could be surround cameras, just cameras. And we know that it's possible because humans is a proof of concept, right? We have eyes and we have a computer, which is our brain, and with that's enough to drive. So do a subsystem only with cameras, a full stack from cameras and to full control just using camera inputs, and then you do another subsystem using other sensors. LiDARs and radars together can form a subsystem which you can use separately from cameras. Now, let's assume that those are statistically independent. It's tricky to prove, and they are actually not statistically independent, but they are kind of independent because radars and LiDARs, different modality from cameras. But if they were independent, this is why I put an approximation there, then the MTBF is a product of the two when you're talking about the probability of a false negative. So instead of proving a miss once every 10 to the power of 7 hours of driving, you'll need to prove it only 1 to the 10, a square root of it, 10 to the power of 3.5, which is about 3,000 hours. You know, 3,000 hours of driving is something quite reasonable to prove performance on. So this is the approach of the industry. This is the approach of specifically what we are doing in using completely separate redundant subsystems because of the validation challenge. So what we have here is a validation challenge that is being solved using redundancies. So let me show you a couple of examples. What you see here, the blue car is the autonomous car, and at some point it's going to detect a pedestrian coming out, a driver coming out of the car. You can see this and now because it detected that there's a blockage, it starts changing lane. The red and the green is green. It would be nice to run this again. So what was happening here, and the next clip we'll see it again, is when the system decided to change lane, it will start color coding the other vehicles in red and green. Red means that the system decided to give way to that vehicle, and green, the system decided to take way from the vehicle. But this decision is 10 times per second this decision is made. So a vehicle that's colored green can be colored red because that vehicle did not allow us to take way. And the system gives way and then makes a decision again and again and again. And what you saw there is that it was very, very dense traffic. Maneuvering in very, very dense traffic is tricky. And with this layer of RSS, you can do that while guaranteeing that you're never going to create an accident. Let's look at the next clip. And remember this red and green, so it will give you an idea. But now we'll start looking how this looks from a top view, from a drone. So there's a car that's blocking traffic, and the blue car with the Mobileye logo on the roof is the robotic car. And you see that all cars are now changing lanes in order to continue the flow, and it's fighting its way, and it's doing this just quite human-like. Now we are going to see how it looks from inside the cockpit. So on the right-hand side, see the blue car is the autonomous car, and look at the red and the green, right? The green turned into red. Now there's another green. And then it was able to do this maneuver. So being agile and safe at the same time is really tricky. In the last few minutes that I have, I'll go into the next frontier. This is also an area that I'm very, very interested in, both from an academic point of view and also from an industrial point of view, and that's natural language understanding. So when you look at AI successes today, it's all narrow domains. An AI system can play chess, can play Go, can drive a car, but it's not transferable from domain to domain. A single task, a single domain, and very, very beautiful things, very, very impressive things can be done with this narrow AI. But really, the promise of AI lies in being able to instill broad intelligence into systems. And this is really far away. And natural language understanding or reading comprehension specifically, like a question and answering tasks, is also a microcosmos to broad intelligence challenge. Because if we can read a book like War and Peace or Game of Thrones and answer probing questions about the plot, about the characters, what they're doing, why they're doing, and so forth, we must capture some broad intelligence there. And it's also something very, very useful to be able to do from an application point of view, but also it's a big step from narrow AI to be able to read a book and answer probing a question. Imagine, reading comprehension tests in SAT. These are very difficult tests if you look at them. No computer can do that today. But what is happening recently is very, very similar to what happened to pattern recognition back in 2012. So in 2012, there was a data set called ImageNet, which is a simple, compared to the complexity of visual perception, is a simple task, but for computers was very, very difficult, in which you had millions of pictures, and in each picture there's an object out of 1,000 categories, and the computer had to tell for each picture what is the object category in that picture. And then deep networks really, tipped everything. And then within a couple of years, the performance of computers on this particular data set reached human-level perception. It's not that computers have human-level perception on broad perception, but on that particular task, computers beat human. So the same thing is happening also with reading comprehension. Specifically, that there is a task from Stanford called SQUAD, Stanford Question and Answering Data Set. It's a very, again, compared to reading comprehension, it's a very, very simple task, but it was quite difficult for computers until recently. So the task is, you receive a paragraph, you receive a free text, an unstructured question on this particular paragraph, and the answer is a span. It is a subset of the paragraph. It could be a word in the paragraph, it could be from word 13 to word 19 in the paragraph, but it's a span, it's a subset of the paragraph. And here computers, specifically a network by Google called BERT, but it's a deep network. There's no special bells and whistles. There are no special, mind-boggling new development in deep networks there. It's the regular deep networks people use, has achieved human-level performance on this particular data set. So we are at a point which is kind of similar to where pattern recognition was back in 2012 in reading comprehension. Of course, now there's a new data set, also coming from Google, it's called the NQ, natural questions, in which computers are not very good at. Okay? So the question is what is required to go beyond simple Q&A tasks? So if we look at the deep networks, there's the issue of expressiveness. So deep networks are sufficiently expressive. That's not really the bottleneck. The bottleneck is inductive bias. That means inductive bias is what assumptions of the nature of the problem we instill into the architecture of the network. So it turns out that with pattern recognition, we were simply lucky. Now, if you look at the way convolutional networks are built, the connectivity and the pooling geometry, it's really tied to the kind of biases you have in pictures, you have in pattern recognition. And this is something that we published a year ago at ICML. So with pattern recognition, we're simply lucky. These networks are simply designed for this task. But when you look at reading comprehension, the kind of inductive bias for NLU could be completely different. You need to find ways in instilling knowledge representations, kind of the AI of the past, which was rule-based AI, knowledge representations as inductive biases into these deep networks if you want to make a big jump in the performance, going from simple QA tasks to true reading comprehension. So if I summarize the takeaways, one is that narrow AI is progressing rapidly. It's really being taken over by industry. There are lots of contributions from the scientific community, but as David mentioned, it's all about resources and data with narrow AI. The state of the art is almost good enough to disrupt entire industries, and transportation, autonomous driving is one of them. When you look at autonomous driving, it's really the ultimate challenge for narrow AI. It combines many different AI tasks, supervised learning, reinforcement learning, ethics of AI, multi-agent decision-making, and it's one of the most challenging narrow AI task that there is today. General AI or broader AI doesn't exist today. And the gap is quite big, and reading comprehension is a good proxy. It's a good proxy for asking questions about broad AI. Because again, if you can read a book and answer questions, probing questions, you probably understood the book in some manner, and it would in some manner represent a broad intelligence. And we think that this NLU is a worthy sandbox to moving beyond AI, and the real key is inductive bias. Here we are not as lucky as we were with pattern recognition, and this is where scientific research can have a big advantage, because just taking the existing deep networks and banging them again and again and again would lead results, but would never solve the real problem of reading comprehension. Some real scientific breakthroughs are required there. Okay, thank you.
So we have time for questions if anyone in the audience would have questions for Professor Shashua. And there are microphones, so you just go to the right place and you can ask your question.
Thank you for a very interesting talk. I have a question about the perception part. You have a lot of information coming in. A lot of it is irrelevant. Do you use attention or do anything to distinguish the relevant from the irrelevant perception?
Well, when we look at the perception, we break it down to different modules. One module is, we call this the object detection module. So anything that you can put a bounding box around it. That could be vehicles, bicycles, pedestrians. We separate static objects and dynamic objects, so you can have also a blockage, a parking car that's being detected as well. The second part of perception is not bounding box-based detections. It's more holistic. Where is a drivable path that you have in the scene? Sometimes it is based on finding the lanes, but sometimes you don't have any lanes in the scene, yet still you know, as a human, you know where the drivable path is. So it's kind of a holistic image coming in, output is a drivable path. And every module that I mentioned, the tool behind it is deep networks. Another module is the free space. Tell me as a robotic agent, where are the areas that I can drive and where are the areas I cannot drive? What is blocking me? And blocking me could be a dynamic object, could be a road edge, could be a curb. It's also something that is blocking me. That's also an area that, again, a tool there is a deep learning. So the problem of perception, and then there's traffic signs and traffic lights. These are different models. So you have a number of models. Each one is trained as a deep network, but has a different task. And then the integration of the outputs of these models gives you the perception. And when you're talking about lots and lots of distractors or irrelevant data, that's the strength of the deep networks. They are able to take a complicated input as a complicated image as an input and find out the relevant data out of it and give you the output. Yep.
Professor Sharma, University of Maryland. In the first part of your talk, when you're describing traditional machine learning, you are describing the hypothesis space and modeling. So that seems like more of a parametric modeling, in the sense you have a set of parameters and you want to optimize, and these parameters are decided by your understanding of the first principles or something on those lines. So you're limiting your model in that sense. And non-parametric modeling, in which you do not have to assume parameters, and that seem to be more compatible with big data, because we expect that the more data you have, more new phenomena you will discover, which will not be in the models that you have. So are this kind of approaches advancing, or would you consider these as deep learning? And in general, when does that learning method become a deep learning? That's
okay. So first, deep networks is really a network is a parametric model. The parameters are the weights of the edges of the network, and it's a hypothesis space that is new, because before deep networks, the kinds of hypothesis space of parametric models that were very, very successful were linear spaces, linear hypothesis spaces, with the kernel trick that enabled us to have nonlinear functions. What is the mystery behind a deep network as a parametric model is that when you increase the amount of parameters to much, much higher levels than you need, you would expect that you will overfit, that you'll not generalize, but actually you do generalize. This is now with non-parametric models have been in existence for decades, and are useful. But deep networks is a tool that created a disruption, and this is why the entire community is focused on deep networks, because with deep networks we can do today what we couldn't do in the past with non-parametric models or with the support vector machine linear models. And this is why all the focus in terms of thinking about those mysteries are focused on deep networks. What makes it deep is the number of layers, and there are mysteries around that as well, but those mysteries have been solved in the last years. This is why I did not mention, for example, why depth is important was a mystery for the past few years, but has been solved by a number of researchers, including in my own lab as well.
At the end of the talk, you started discussing your thoughts on, where things are going in terms of broadening AI capabilities beyond narrow domains, and you were talking about the importance of natural language understanding for doing this. To what extent do you believe physical environmental modeling does or doesn't play a role, like actively maintaining simplified models of the environments? For example, isn't natural language, as humans use it, just kind of a tool based on encoding representations of our environment? Do you think these things need to be explicitly taken into account as we try to make more robust AI models, or can it all just kind of happen implicitly inside a black box, as we've been doing?
Well, the hope is that it can all happen inside a black box, but I would suspect it's not going to be one black box in which a text is entered and reading comprehension is outputted from that one single black box. Just like in perception, as I mentioned before, we have many different, it's broken down into many different components all working together. Each one of them is a black box, but all together, these are different components. I believe that with reading comprehension, something like this would be happen, kind of multitasking, different modules that each one of them is specializing, one maybe in the temporal domain, the other one in verb senses and separating verbs from nouns and so forth and so forth. But each of those, the hope is going to be a black box, is that the representations are implicit. This is the beauty of deep learning. And the recent successes, like with Squad, even though the task is rather simple compared to reading comprehension, it was a very, very difficult task without deep learning. So the hope is that these black boxes you can push the envelope of these black boxes much, much further than narrow AI. That's the hope.
Thank you.
So I agree with you that for natural language understanding, it's key to incorporate knowledge representation into the architecture of the network. So my question is, how do you propose to do that?
Maybe a year and a half from now, I'll be able to show you. This is something that we're working on very, very diligently, both in academia, also in my investments in other companies. That at this point, I'm not at the position to make it public. But this is an area that I feel very, very strongly that could be the next big thing.
Professor Simoncelli.
Thanks for that talk. I have a question that I think was implicit in several of the previous questions, and I wanted to make it more explicit. A lot of what you described really relies on coming up with a greatly reduced description of the environment that you, the investigator or the researcher or the developer of a technology has decided or knows in advance is the sort of right language for solving the problem. So in driving, that corresponds to knowing the position and speeds of the cars around you and knowing gaps between them and various things that you need in order to perform the driving task. So you're really relying very heavily on knowing what that set of parameters is that you need to estimate, and that turns the perception problem, as you called it, into a mapping from the vast input space of pixels coming into a camera and other measurement devices, mapping those into this small, low-dimensional parameter space. And of course, we all know that the deep learning literature is built on that idea, using supervised learning to establish that mapping and do a good job of it. So my questions for you are, the specific question is, how do you know that the set of variables that you've prescribed for the driving problem are the right set of variables? How do you know that you're not missing something that is important, let's say to a human being, but you have failed to include it in your repertoire? And then the more general question is, in what sense should we believe, or do you believe, that the driving problem really offers a prescription for how to solve all AI problems? Because I think there are many problems that humans solve where we don't know what the relevant variables are. We may have a partial guess of that, but we can't really establish a definitive list. And it may be that there's not really a definitive list.
Okay, so I think autonomous driving is an example in which one of the inductive biases is prior information. The fact that we all know what it means to drive gives us a very, very powerful advantage of describing that kind of inductive bias as a prior information. The way you break down the problem into modules, that's a very, very strong prior. Because otherwise you can think of kind of an end-to-end system in which you have images in, let's assume we're only looking at cameras, images in and output is the steering command. You can think of it in that way.
That's essentially what you've done for the perception end of your system. You've made that end-to-end.
No, we didn't make that end-to-end. We made several modules, each one of them end-to-end. Right? So it's not that there is one network in which images come in and control of the car comes out. And a couple of years ago, we wrote a paper why something like this cannot be done. You can never validate it. The sample complexity of it would be too high. You use prior information, to break this down into different modules. Each module is trained end to end, but it's different. Right? A module of object detection, a module of drivable path, that's prior information. Now, whether that prior information is correct or not is yet to be proven. But if you can drive and you can validate probability of an accident better than humans, then that would be sufficient. And this is why I mentioned the perception challenge versus the driving policy challenge. If you look at it as one challenge, it would be almost impossible to validate, because then you cannot decompose this into different subsystems, because driving policy is one system. But if you can then build a model in which you guarantee that if your perception is correct, you'll never make an accident, then you remove that out of the equation, and the only thing that you need to validate is your perception. What is the probability of making a perception mistake that will lead to an accident? And this is something that you can verify statistically if you create separate subsystems. If it's one subsystem, it's outside of the realm of our validation capabilities. Now, whether the last part of your question, whether this can be a prescription for general AI, I think autonomous driving is a very, very good problem of narrow AI. I don't see how it generalizes to other domains. It is interesting in the sense that it's one of those problems in which you have also to handle ethics. And this is what I mentioned about guaranteeing probabilities of accidents. Normally, when people deal with the AI, there are no ethics involved. There's no need for ethics. Society is gradually coming to the point in which, from privacy perspectives, you want to start thinking about ethics. But from a technologist, ethics is something that doesn't give you any contribution. But when you think about autonomous driving, without guarantees, you can never put a car on the road, because if an accident will happen, what should you do? Right? Nobody wants to go to jail. So ethics becomes a critical issue when developing AI for autonomous driving.
So we're running late. George, why you get the last question, but please.
Okay. The talk was very interesting, but it isn't clear to me how it relates to the science of deep learning. That is, what can you say about how we should change the way in which we think about machine learning so that it becomes more structured and we have a better understanding of whether what we have said is really true?
Well, this is it opens a deep philosophical. Deep learning, the rise of deep learning is a testament for failure of the scientific method. What does this mean? Let's think about it. Why do we need deep learning? Because we came to the conclusion, we as a society of people who try to build things, we came to the conclusion that there are certain problems that are unsimplifiable. Right? Unlike physics, right? Physicists took, a very, very wide phenomenon and reduced it into a number of mechanical laws, of electromagnetic laws and so forth. Reduced a very, very complicated problem into basic principles. With computer vision, we were not able to do that. In pattern recognition, we were not able to do that. For decades, we were building modules of how to describe the world in a reduced manner in order to write algorithms to do computer vision tasks, and we were never successful until the rise, successful in terms of reaching anything useful, anything that is even close to human perception in narrow tasks. And with deep networks, we were able to do it. Now, it's not only in computer vision. It's also in NLP, natural language processing, voice to text, the kinds of, Siri, Cortana, Alexa that we communicate with. Many problems in biology and other areas of science that we start seeing success because of the failure of the scientific method in trying to find a reduced set of principles.
Excuse me, there are different metrics. In science, the metric for success is the ability to predict. you have in machine learning another metric, which is how accurately can you perform your task. So it isn't that you have a failure of the scientific method. They have different measures of success. So the question is, how can you more intelligently do the kind of thing that you're doing?
I'm afraid I have to cut off the discussion at that point. It's a very interesting question.
It was the most interesting question.
But, yeah. Thank you very
Okay,
much,
thank you,
Professor Shashua.